You've probably heard of the Atacama Desert in Chile. It's one of the driest places on Earth, so dry that only life forms adapted to brutal conditions can survive there. Parts of the Atacama are even used as test grounds for Mars missions because its arid climate resembles Mars. With all those traits, it might look like the last place an ordinary person would want to visit, but for astronomers, it's basically a paradise. It offers a clear sky almost all year, at least 330 cloudless nights, and there are no nearby settlements. That means no light sources polluting the sky. All of this makes the Atacama Desert one of the best places on Earth for sky observations and professional telescopes. Giants like the VLT, Gemini South, and the 39-meter ELT now being built are perched on the Atacama's high peaks. After dark, it's one of the darkest places on the planet, where using any light source is completely forbidden. And on the top of a mountain in this desert, at an altitude of about 2,600 meters, a new telescope has opened its eyes to the sky, the VERA RUBIN telescope. But this telescope is unlike anything we've known before. In fact, whether you're into astronomy or not, it's pretty wild to think that a telescope sitting thousands of miles away on a mountaintop in one of the darkest regions on Earth could one day even save your life. When you hear telescope, what comes to mind? Most of us probably think of telescopes as instruments that let us look closely at very distant objects. But that's not quite right. A telescope's main job isn't to zoom in, it's to collect light from celestial objects. Of course, to use the light they collect effectively, telescopes can be designed with different fields of view. Think about the James Webb Space Telescope. It can resolve extremely distant galaxies in detail, but it sacrifices field of view to do that. For example, JWST's image of the galaxy cluster SMACS 0723, some 4.6 billion light-years away, covered a patch of sky roughly the size of a grain of sand held at arm's length. In rough terms, telescopes like James Webb or the Hubble Space Telescope can see only a very small portion of the sky at once. Even though they can peer into the deepest reaches of the universe, their narrow fields of view mean they also miss a lot of what's happening across the sky. There's another class of instruments, though, unlike those target-focused telescopes, that have a very wide field of view and can image huge swaths of the sky at a time. In astronomy, we call these survey telescopes. As a comparison, with binoculars, you see a wider area of the sky than with a telescope, but you can't see objects as close up. Now imagine you could watch a very wide area of the sky and still collect enough light to see objects millions of light years away. Sounds like a pipe dream, but the VERA RUBIN telescope is built to do exactly that. VERA RUBIN cost about $1 billion to build, and there are two core reasons it can pull this off. First, it houses the largest digital camera on Earth, about the size of a car, with a resolution of 3,200 megapixels, i.e., 3.2 gigapixels. To grasp how extreme that is, consider this. I couldn't show you any Rubin image at full size in this video even if I wanted to. Even if I found a way to embed the originals at full resolution, you'd need a wall made of around 400 4K TVs to see them at native detail, or a screen about 50 times the size of a movie theater screen. Thankfully, we don't need to view them at full native resolution. That extreme resolution means you can keep zooming in with almost no loss of detail. Of course, this isn't just the camera's magic. You also need a telescope that can collect light from very far away and deliver it to that camera. With its 8.4-meter primary mirror and a special 3-mirror design paired with that camera, Rubin can capture in a single shot an area of the sky larger than 40 full moons. And its images aren't limited to that single field. You can stitch together shots from different regions of the sky. What makes Rubin so critical is precisely this massive field of view. If you can observe such a huge area of sky for a long time, you can image millions of galaxies in that region and see how they change over time. Combine a telescope that can sweep such broad areas with a 3.2 gigapixel camera and 6 color filters, then take roughly 1,100 separate exposures of the same region and stack them. And something incredible happens. You get a 3 trillion pixel photograph of space. One of Vera Rubin's first images released to us on June 23rd shows the Virgo cluster, which contains roughly 1,000 galaxies. In that frame, we're seeing an area more than 70 times the apparent size of the full moon. A 3 trillion pixel image is packed with detail at every point. Remember, the galaxies in the Virgo cluster are gravitationally interacting with one another, and each of those showpiece galaxies contains trillions of stars. So this single image lets us view the depths of the universe from a remarkably wide perspective. It's a reminder that every tiny patch of sky is filled with galaxies, whether we notice it or not. Since we can't reasonably display the full native image in this video, there's a website that lets us zoom in and explore details interactively, and that's what we'll use here. Let's look more closely at some of the highlights. One of the cluster's brightest members is Messier 49, a 150,000 light-year-wide elliptical galaxy. Astronomers often call elliptical galaxies dead galaxies because star formation has mostly stopped and the population is dominated by older, redder stars, giving giants like M49 their reddish hue. To the left of Messier 49, the bluish color, face-on orientation, and overall resemblance to our own galaxy draw your eye to a spiral named NGC 4535. Unlike an old red elliptical, this spiral is actively forming stars in its gas and dust-rich arms, so it glows in hot blue-white tones. With its face-on angle, perhaps the most photogenic detail in the image is Messier 61. You can see its bright core and spiral arms clearly. That intense central brightness is driven by a supermassive black hole. Since our Milky Way is also a spiral, this is a great example of what our home might look like if we could view it from the outside. Near Messier 61, we run into another spiral, NGC 4301. Near, of course, is deceiving. These fields span tens of millions of light years, so even close neighbors can be separated by vast distances. Another pair can trick us the same way. They look like they're merging, but one is much farther away. The galaxy on the right, NGC 4411, is 50 million light-years distant, while its apparent companion, NGC 4411b to the left, lies over 70 million light-years away. That said, the image also contains true close pairs and mergers. For example, these 3 galaxies really are in the process of merging, and you can even see evidence of gas and dust being exchanged between them. Mergers like this are common in the universe, but catching a 3-way interaction in a single field is still a treat. Wherever we move in the image, we run into hundreds of galaxies at all angles, types, and colors. Now for one of the most striking aspects. When you zoom deeper, the background fills with tiny points that look like stars. But at the distances involved here, almost none of those specks are stars. They're background galaxies, each containing its own trillions of stars and planets. Across the entire image, there are more than 10 million galaxies. In other words, in this field, we're actually seeing far more galaxies than individual stars. Now that we have a handle on Rubin's capabilities, what if we point it toward the center of our own galaxy, where gas and dust are thick? One of those clouds is the Lagoon Nebula. Even at 4,000 light-years away, the lagoon is bright enough to spot with the naked eye. For astronomers, it's an open-air lab for studying the early stages of star formation and the sculpting of gas by infant stars. In Rubin's image, we're looking at just 7 hours of exposure. As you may recall from earlier videos, the longer the exposure, the more detail you recover. Rubin can pull this much structure out of the lagoon in just 7 hours. The swaths of red show the lagoon proper, and the yellowish glow in the center is the combined light of millions of stars. Zoom in and you can resolve many of those stars individually. The dark lanes around the nebula are material ejected in the depths of massive stars. These dense clouds are so opaque they block the starlight behind them. In the upper right sits another nebula, the Trifid. Hydrogen gas lit by bright young stars shines red, while massive stars create that bluish reflection glow around the cloud. These are top-tier images, visually and technically. And remember, these are still test shots. Rubin hasn't even fully begun its scientific surveys. Over the next 10 years, the VERA RUBIN telescope will shoot hundreds of images of the sky every single night. Given how quickly Rubin can cover wide areas, it will effectively create a movie of the sky. Think about it. The sky looks still to us, but it's constantly changing. Everything from planets to galaxies is in motion. With target-focused telescopes like JWST, we can't take in the sky as a whole when tracking moving objects. It's like staring at a few pixels in a 4K movie. Rubin, by contrast, can monitor regions more than 40 full moons wide and then revisit them quickly, revealing how the sky changes over time. In other words, Rubin can literally film the sky. About 80 years ago, the astronomer Fritz Zwicky observed galaxies in the Coma cluster and found they were moving far too fast. Their speeds suggested the cluster should fly apart. And yet, somehow they stayed bound together, as if held by some mass that neither emits nor reflects light. That was the first observational hint of dark matter, but it wasn't conclusive. Then, on November 14, 1977, a woman astronomer named Vera Rubin made a set of pivotal measurements. She carefully studied the rotation of about 60 spiral galaxies, including Andromeda. In all of them, she found something bizarre. Stars far from the center were orbiting just as fast as stars near the center. That was shocking. By gravity's rules, stars farther from the center should orbit more slowly, like in our own solar system, where outer planets like Uranus and Neptune move more slowly than inner ones. In every spiral Rubin measured, the outskirts were moving much faster than expected. So fast, in fact, that the galaxies shouldn't even exist. They should have torn themselves apart. Her results were checked by astronomers worldwide and held up. Other observations revealed that entire galaxy clusters showed the same discrepancy. The implication was inescapable. There must be invisible mass, dark matter, holding galaxies and clusters together. Since then, thousands of observations have led astronomers to estimate that dark matter makes up about 80% of all matter in the universe. And yet, despite all those telescopes and all that data, we still don't know exactly what dark matter is. Pinning that down is one of Rubin's main goals. So how can Rubin do what other telescopes can't? Its core technique in the hunt for dark matter will be gravitational lensing. As light from distant galaxies travels through the universe, the presence of mass, including dark matter, bends its path. In that sense, dark matter acts like a cosmic magnifying glass. By measuring how the light is bent, astronomers can map the distribution of dark matter. Hubble and James Webb have observed lensing many times, of course. But unlike them, Rubin can cover enormous areas quickly. It won't look at hundreds of galaxies or even millions. It will look at billions. Rubin will carry out the largest galaxy survey ever attempted, providing our strongest data yet on how dark matter is spread through the cosmos. Rubin can capture a field more than 40 moon widths wide in one shot, and it's designed to shift that field every 34 seconds. Yes, just 34 seconds. That means that roughly every 3 nights, astronomers can scan the entire visible sky. Over the survey, Rubin will revisit each galaxy about 800 times. Repeated observations like that will refine our understanding of how dark matter shapes galaxies. And because light has a finite speed, looking at faraway galaxies means looking back in time. So these time series observations will also show how dark matter and dark energy have shaped the universe over cosmic time. We're not using movie of the universe as a throwaway line. That's really what Rubin will deliver. The first image with over 10 million galaxies already hints at that. A telescope that can sweep huge areas quickly and still reach very faint objects also becomes an asteroid hunter. Asteroids are rocky or metallic bodies in solar orbits. Most live in the main belt, but some come close to Earth and can be potentially hazardous. The first step in preventing an impact is to find them, but that's harder than it sounds. The sky is enormous, and asteroids are among the faintest things in it. Worse, unless you can stack multiple images of the same region, you can look right at one and still miss it. I don't want to spook you, but it's entirely possible that a large, fast asteroid capable of wiping out our planet is on a collision path right now, and we just haven't found it yet. Rubin is powerful enough to spot thousands of asteroids in a single exposure. In fact, even in the very first test image, over 2,000 asteroids were detected. In the interactive viewer, if you toggle the asteroid filter, you can see their trails all across the field. 2,000 in one go. Over the next decade, Rubin is expected to discover about 3.7 million asteroids in our solar system. For reference, we've found roughly 1 million to date. Rubin alone could triple or quadruple that number. Most will be harmless main belt asteroids, but we're also very likely to find many that will pass close to Earth, and some that could be dangerous. That's why Rubin isn't just revolutionary for dark matter and galaxy science. It matters for the future of our planet. If, among millions of asteroids, one truly large and dangerous Earth impactor is found, what happens next will depend on where missions like DART, designed to alter asteroid orbits, have gotten by then. Assuming, of course, that the petty ambitions of those unaware that we live on a dust speck among billions of galaxies don't derail that work first. See you in a different corner of the universe in the next video. Take care.